All right, let's finish up this 5.2 that is so very long. The last part of 5.2 covers trigonometric functions of any angle. Now, in 5.2, we got the definitions of the trigonometric functions in terms of ratios of sides of a right triangle. If we had a right triangle and we labeled one of the acute angles theta, if we label the side opposite theta A and the side adjacent to theta B and the hypotenuse C, we could form 6 different ratios with A, B, and C, and those 6 different ratios are the 6 trigonometric functions. I'll just write down the first 3. The way I have that triangle labeled, sine of theta would be opposite over hypotenuse, A over C. And cosine of theta would be adjacent over hypotenuse, B over C. And tangent theta is opposite over adjacent, or A over B. And then, of course, you could write cosecant, the reciprocal of sine, secant, the reciprocal of cosine, and cotangent, the reciprocal of tangent. But so far, we have only talked about trigonometric functions in terms of this right triangle, ratios of side of a right triangle. Well, what if we wanted to, instead of talking about ratios of sides of a right triangle, what if we had some angle in the Cartesian coordinate system, because we've already talked about angles in the Cartesian coordinate system. Standard position is putting the initial side on the positive x-axis and then rotating the terminal side to some point. We can think of that as being an angle theta, just like we thought of that being an angle theta. And notice no matter where that terminal side is, there's going to be a point on the terminal side, and we can label that point X, Y. And what we're trying to do is take the 6 definitions that we already know and somehow apply them to any angle in the Cartesian coordinate system. Notice that no matter in what quadrant my terminal side lies, I could drop a vertical line, or if I was in quadrant 3 or 4, I could raise a vertical line that would be perpendicular to the x-axis. And if I either drop or raise that line that's perpendicular to the x-axis, all of a sudden I have something that looks a whole lot like this. I've created a right triangle. And the radius of the circle, if this was a circle, its radius, we could just call it R. What would this horizontal distance be from the origin to this line that I dropped straight down to the x-axis? What's that horizontal distance? Well, that distance is x, because x is the x-coordinate of that ordered pair. And this vertical distance is y. So if we wanted to talk about the trigonometric functions of this angle in the Cartesian coordinate system, instead of this angle in the right triangle, we could still say that sine of theta would be opposite over hypotenuse, y over r. And cosine of theta would be adjacent over hypotenuse, or x over r. And tangent of theta would be opposite over adjacent, or y over x. And then, of course, we could write what would give us cosecant theta, secant theta, and cotangent theta. But we've just expanded our definition of these trigonometric ratios beyond simply triangles. We now have them defined as functions of functions of a point on any side. Let me try that one more time. Functions of a point in the Cartesian coordinate system. Now, here I made my point in the first quadrant, but to show you something from the book, if my point was in the second quadrant, I could still drop a vertical line straight down to the x-axis. This horizontal distance would be x. This vertical distance would be y. R would still be my hypotenuse. And if I started in standard position and rotated to that terminal side, that's way too big, to that terminal side, then actually this is angle theta, but it's not, I don't know why they don't put it in this section, they put it in the next section. They call this the reference angle for theta. And the trigonometric functions of theta are the same as the trigonometric functions of the reference angle, except for the SIGN sign, except for the signs of the X and the Y. The trigonometric functions of this reference angle would be the same as the trigonometric functions of our original theta, except for my X's would be negative here, where my X's had been positive here. If my point was in the third quadrant, I could raise a vertical line up to the x-axis, and I would still have the horizontal distance being x, the vertical distance being y, and I could form the 6 trigonometric functions with that. Same thing if my terminal point was in the fourth quadrant. So here are our, I'm sorry, I have trouble with mirror images. Here are our definitions of trigonometric functions of any angle in the Cartesian coordinate system. No matter where your terminal point is, some terminal point x, y can be any point other than the origin, and the sine would be y over r, the cosine would be x over r, the tangent would be y over x, and then here are my 3 reciprocal functions. Now, one other thing to point out is that if my horizontal distance is x and my vertical distance is y, then I can find r with the Pythagorean theorem. R squared would be x squared plus y squared. So r would be the square root of x squared plus y squared. Let's see how we're going to use this on a few problems. And I think you have room to write on your notes here. Sorry. On number 76, we have a function. Or not a function, we have a point on the terminal side of an angle that is in standard position. What quadrant is that point in? Since the x and y are both negative, it's in the third quadrant. I don't know exactly where in the third quadrant. I suspect I'm not doing this to scale, but that's my point P in the third quadrant, and I can raise a vertical line up to the x-axis, and I have created a right triangle with some angle theta. Now, I hate to label a side of a triangle as being negative technically a length can't be negative, but still, I'm going to label this side adjacent to theta. That's my horizontal distance. I'm going to label it -8, just so I don't lose the negative. And -15 is this vertical distance. So I'm going to label it -15. And then we can find the length of the hypotenuse by the Pythagorean theorem. The length of the hypotenuse would be the square root of 64 plus 225. That's the square root of 289, and that's 17. So we have a -8, -15, 17 Pythagorean triple. Now that little angle that I created and labeled theta, I could say the sine of theta is opposite over hypotenuse, -15 over 17. Cosine of theta is adjacent over hypotenuse, -8 over 17. And tangent theta is opposite over adjacent, -15 over -8. That's just 15/8. And then I could find these three reciprocal functions. All right, let's do one more of these. If P is a point on the terminal side of an angle in the Cartesian coordinate system that is in standard position, that point P is in the second quadrant because X is negative and Y is positive. I can drop a line straight down to the nearest x-axis, connect that point to the origin for the terminal side of that angle, and I've created a right triangle. If that point is the point -2, 3, then this horizontal distance is 2. I'm going to write -2 just so I don't lose the fact that it's in the second quadrant, and that vertical distance is 3. You can tell that my picture's not to scale because it looks like the horizontal side is longer than the vertical side, and obviously it's not supposed to be. We can find the hypotenuse with the Pythagorean theorem. It'd be the square root of leg square plus leg square, square root of 9 plus 4, or square root of 13. Here's the angle theta that I've created. And sine of theta would be opposite over hypotenuse. Cosine of theta would be adjacent over hypotenuse. And tangent would be opposite over adjacent. And then you would have the three reciprocal functions. All right, we are almost through. I think I need to do 4 more problems. Actually, on number 86, I just want you to use your unit circle that you've drawn to find the 6 trigonometric functions of these 4 angles. They're all quadrantal angles, which means they lie on the terminal side lies on either the X or the Y axis. If you pull out the beautiful well-labeled unit circle that you have and look, let's say at the D part, 5/2 pi, you just have to figure out where 5/2 pi is. Here's 1/2, 2/2, 3/2, 4/2, 5/2. 5/2 is on pi is on the positive Y axis, and the ordered pair on the positive Y axis is 0, 1. I'm having a seriously dyslexic time. If the ordered pair is 0, 1, oh, well, what's the radius? The radius of this circle is square root of x squared plus y squared. The radius of this circle is 1. So the sine of 5/2 pi is y over r, or just 1. The cosine of 5/2 pi is x over r, or 0 over 1, which is just 0. And the tangent of 5/2 pi is the y over the x. What would you say about that? Tangent of 5/2 pi, all we can say is it's undefined. 1 over 0 is undefined. Not sure what just happened there. So since you're using your unit circle, I'm not going to do all 3 parts of that. Last 2 kinds of problems. Number 88 says, find the quadrant given theta, or containing theta, if the given conditions are true. Well, I want you to think about the signs of all the ordered pairs in each of the quadrants. In the first quadrant, both the x and y are positive. Go ahead and label the sign of the coordinates in the other 3 quadrants. That's what you should have. So we're trying to find what angle or what quadrant theta has to be in the A part if tangent is negative and cosine is positive. Now, when I ask you what is sine of theta in the first quadrant, you're going to think, well, sine is the y over the x. Y over x, I may have said the wrong thing there. You're going to think tangent is y over x. And in the first quadrant, y over x would give you a positive. If I said, where is tangent negative? In which 2 quadrants, if you divided the y by the x, would you get a negative answer? Second quadrant, when you divide a positive by a negative, or fourth quadrant, when you divide a negative by a positive. So this could either be quadrant 2 or quadrant 4. But what about the quadrants in which cosine is positive? Cosine is your x over r. And if your radius is square root of a squared plus b squared, your radius is always positive. So you really only need to find where your x's are positive, and your x's are positive in the first quadrant and the fourth quadrant. So if tangent is negative in the second and fourth quadrant, and cosine is positive in the first and fourth quadrant, what single quadrant satisfies both conditions? The quadrant that satisfies both of those conditions is quadrant 4. That's the only quadrant where tangent is negative and cosine is positive. In the B part, we want to know where secant is positive and tangent is negative. Well, secant is the reciprocal of cosine. Cosine is x over r. So secant is r over x. But again, the radius is always positive. So where is your x positive? We're looking for where secant's positive. That's going to be wherever x is positive. And that is quadrant 1 or quadrant 4. Tangent is your y over your x, and we want to know where tangent is negative. Wherever you divide the y by the x and get a negative answer. Well, that's the same as we had here, quadrant 2 or quadrant 4. So what single quadrant satisfies both conditions? It just happens to be quadrant 4 again. That makes sense because both of these problems had tangent being negative, and wherever cosine is positive, secant's going to be positive as well. All right, C part. We want to know where cosecant is positive and cotangent is negative. I'm thinking cosecant is the reciprocal of sine. Sine is y over r. So cosecant is r over y. But we know r is always positive. So we're really only looking for the quadrants where y is positive. And y is positive in the first quadrant and the second quadrant. We're also looking for where cotangent is negative. If tangent is y over x, then cotangent is x over y. Where in the Cartesian coordinate system would the x divided by the y give you a negative? Well, negative divided by a positive is a negative. Positive divided by a negative is a negative. So that's quadrant 2 or quadrant 4. And the one quadrant that satisfies both of those conditions is quadrant 2. All right, last kind of problem. 2 more examples. 90 and 92 say use the fundamental identities to find the values of the trigonometric functions for the given conditions. We're given 2 conditions in number 90. We're told that cosine is negative and cotangent of some angle theta is 3/4. So like we did on the previous problems, I'm going to think if cosine is negative and cosine is x over r, then I'm looking for where my x's are negative. And my x's are negative in the second and the third quadrants. And what can I do with the fact that cotangent theta is 3/4? Well, I know that tangent theta is y divided by x, so cotangent theta is x divided by y. Now, if cosine's going to be negative in either second quadrant or third quadrant, where is cotangent positive? Where could you divide the x by the y and get a positive? That would be the first quadrant or the third quadrant. A positive divided by a positive, or a negative divided by a negative. So now at least we know in what quadrant theta lies. If cotangent's going to be positive and cosine's going to be negative, then theta must be a third quadrant angle, because that's what satisfies both of those conditions. I'm going to draw me a third quadrant angle raise a vertical line to the nearest x-axis, and I've created an angle theta. I need to label it in such a way that my x is 3 and my y is 4. That means my adjacent side is 3 and my opposite side is 4. Except for the fact that I've already determined that this is a third quadrant angle, which means the x and the y both need to be negative. By the Pythagorean theorem, I would get the hypotenuse as 5. Let's check that everything agrees with what we were given. Is the cotangent of my theta 3/4, positive 3/4? Well, here's theta. Cotangent is adjacent over opposite. -3 over -4 is positive 3/4. And the cosine of my theta, the x over r, would be negative also. So I have this triangle labeled correctly. Now I just want to give the other 5 trigonometric values of theta. So I want to find sine theta, cosine theta, tangent theta, cosecant theta, and secant theta. I already know what cotangent theta is. If cotangent theta is 3/4, then tangent theta is 4/3. And sine theta would be opposite over hypotenuse, -4/5. And cosine theta is adjacent over hypotenuse, -3/5. Cosecant is the reciprocal of sine, and secant is the reciprocal of cosine. So if you give me the one trigonometric value of an angle theta, and I can figure out what quadrant theta is in, then I can find the other 5 trigonometric functions of theta. And 92 is the same thing. Just get you one more example. One of the conditions we're given in number 92 is that sine is negative. Sine is your y coordinate. So your y coordinate is negative in the third and the fourth quadrant. We also know, or are given, that cosine is positive. Cosine's your x. So where is x positive? Well, x is positive in the first and the fourth quadrant. So what single quadrant satisfies both of those conditions? What do you know about theta? It has to be in the fourth quadrant. So I'm going to draw a fourth quadrant angle and raise a vertical line to the nearest x-axis. I'm going to label that acute angle theta. Then I need to label all three sides of this triangle in such a way that cosine of theta is a half. Well, cosine of theta is x over r. That means 1 is x and 2 is r. The radius is 2. The x, the horizontal distance, is 1. And by the Pythagorean theorem, this vertical distance would be the square root of hypotenuse squared minus leg squared, or square root of 4 minus 1, square root of 3. That's almost right. Cosine of theta is 1/2, but the way I've labeled this triangle, sine is not negative. I need to remember that this angle is in the fourth quadrant, so that side opposite theta is negative square root of 3. We have cosine theta, we can find sine theta, tangent theta, cosecant theta, secant theta, and cotangent theta. Sine theta is opposite over hypotenuse, negative square root of 3 over 2. Tangent theta is opposite over adjacent, just negative square root of 3. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. Problems like this on the test, I tell you, you don't have to rationalize the numerator, or excuse me, rationalize the denominator. But if you look in the back of the book and they don't have negative 1 over square root of 3 for cotangent on this problem, just rationalize the denominator and you'd get negative square root of 3 over 3, and that answer would be equally fine. All right, you're ready to finish up day 2 homework. Page 348, odds 51 to 77 and 85 to 91.